A few episodes ago, we looked at the general hardware overview of a modern electronic computer system. Today, we zoom way in and take a look at the fastest memory component, static random access memory. This kind of memory is typically used in CPU registers and caches due to its extreme access speed. However, it is also orders of magnitude more expensive than the alternative, dynamic random access memory typically used in main memory, which is considerably slower than SRAM. It is worth pointing out that generally both SRAM and DRAM are volatile. In other words, they only keep their content when power is supplied. Before we get started, let's get familiar with two types of MOSFETs. By the way, MOSFET is just fancy talk for a type of transistor like this. Notice that it's got three legs. We'll see why shortly. N-type MOSFET, or NMOS, is like a switch controlled by the input voltage. Here we have an NMOS. On the left is the input. From above, we have the power source. Output flows out from the bottom. If the NMOS is powered and we supply a high voltage at the input, the transistor closes and enables electricity to flow from source to output. If we apply a low voltage at the input, the transistor opens and cuts the electricity flow. P-type MOSFET, or PMOS, is also like a switch controlled by the input voltage. However, unlike NMOS, PMOS does the exact opposite. Here we have a PMOS. On the left is the input. From above, we have the power source. Output flows out from the bottom. If the PMOS is powered and we apply a low voltage at the input, the transistor closes and enables electricity to flow from source to output. If we apply a high voltage at the input, the transistor opens and cuts the electricity flow. If we first connect the inputs of an NMOS and a PMOS, then connect the PMOS's output to the NMOS's input, finally connect the output of the NMOS to ground, we have a CMOS, which is a logic converter. It simply negates the input voltage. For instance, if we apply a new voltage at the input, the PMOS closes and allows electricity to freely flow to the output. The NMOS opens and prevents the electricity from emptying to ground. This creates a high voltage at the output, negating the input's low voltage. On the other hand, if we apply a high voltage at the input, the PMOS opens and cuts off the power supply. The NMOS closes and connects the output to ground, draining its voltage. This creates a low voltage at the output, negating the input's high voltage. If we connect the input of a CMOS to the output of another CMOS, and then connect the second CMOS's input to the first CMOS's output, we have a bistable latching circuitry, which forms the basic storage mechanism for SRAM. If the circuit is powered and in standby, it continuously maintains its content. For instance, let's say that CMOS 1's input is high voltage. Its output must be low voltage. This also means the CMOS 2's input is low voltage, which in turn means CMOS 2's output is high voltage, which then feeds back into CMOS 1's input. Any electricity loss is replenished by a power source. To enable reading and writing, one PMOS controlled by the write line is connected to each CMOS's input and output. With the schematic complete, let's now take a look at what happens when we write and read from it. Let's say we want to write 0 to it. First, we set the bit line to 0. This means we also set bit line bar, which is always opposite of bit line, to 1. We charge the bitline bar with a voltage high enough to overcome what the latching circuitry might already contain. Once bitline bar is charged, we assert the write line by applying a high enough voltage such that PMOS 3 and PMOS 4 close, allowing electricity to flow. Electricity flows into the input of CMOS 2, overcoming any previous state. This causes CMOS 2 to output low voltage, which then causes CMOS 1 to output high voltage. Then the write line loses voltage, and at this point the new value is latched in. Now let's read from it. First, both bit lines are pre-charged with a high voltage. Then the write line is asserted, enabling PMOS 3 and PMOS 4. Because CMOS 2 is outputting a low voltage, bit line will experience a voltage drop relative to bitline bar. A sense amplifier then detects the relative voltage change between the two bit lines and outputs the final value. If bit line has a lower voltage than bitline bar, 0 is read. Otherwise, 1 is read. You can see that this implementation of SRAM requires 6 transistors to store 1 bit of information. This is the primary reason why SRAM is so much more expensive than DRAM, which uses far fewer transistors to store the same amount of information. We'll look at DRAM in another episode. Thanks for watching. I'd like to give special thanks to Sous Vide. Do you suck at cooking but want to appear sophisticated? Try Sous Vide. This is an Indian Tribe production, all rights very much reserved.